We've already looked at the limits of functions as they approach a number, or 0 is one we often look at. Now let's look at limits as they approach infinity. That means as x gets bigger forever, as x gets smaller forever, where is the curvature of the graph going? Now we actually already know how to do this. This is called finding a horizontal asymptote. We just didn't call it a horizontal, or we called it a horizontal asymptote the last time we learned it because we hadn't yet learned the term limit. So a horizontal asymptote is really what is the limit as x approaches infinity. And the way that we learned it was that if the biggest exponent of x in the numerator and denominator were the same, then the horizontal asymptote was y equals the ratio of the coefficients. So it turns out that the horizontal asymptote is 1. Since a limit as x approaches infinity is the same thing as a horizontal asymptote, the answer to this problem should be 1. Well, one of the things we're going to do is we're going to look at the graph. So if you graph this on your calculator, remembering to put the numerator and denominator in parentheses, the graph looks something like this. So the question is there a line, or does it look like there is a line here that the graph probably approaches but never touches? And it does. Another thing that you can do is you can go and look at the table. And if you go in the positive x direction, you'll notice that the the y values keep getting bigger, but very slowly. So you have like 0.96, 0.97, 0.98, 0.99, 0.999, 0.9999. So it's happening very slowly. When that happens, it appears as if it's approaching 1, because it can't ever be 1. If you look at the table as you approach x from the negative direction, the same thing is going to happen. The numbers keep getting closer and closer to 1, but very slowly. So the limit as x approaches infinity of x squared minus 1 over x squared plus 1 is going to be 1, because it's the horizontal asymptote. So now let's look at some other graphs. Let's look at the limit as x approaches infinity from the positive direction of 1 over x, and the limit as x approaches negative infinity of 1 over x. This is basically looking at the same graph from two different directions. So one of them is looking at the graph as we go into the positive infinity direction. Well, what I would do is I'd start by graphing this. And 1 over x is really your parent function for rational expressions. It's this graph. So as you look in the positive direction, the graph continuously gets closer and closer to the x-axis. But in order for it to actually hit the x-axis, the y value, the output, would need to be 0. Except that this fraction can't ever equal 0. Because first of all, you can't put 0 in the denominator, so x can't be 0. And in order for the output to equal 0, the numerator would need to be 0. But the numerator is not a variable, so you can't change it. So as we look in the positive direction, it appears as if it's approaching 0. But we know that a limit does not mean that it actually hits it. What if we look from the negative direction? Let's look in this direction. Well, the same thing's going to happen to the graph. And again, if you go and look at the table, what you'll see in both directions, as you go in the positive x direction and the negative x direction, the values of y continuously get smaller and smaller. They become more and more decimally, if that's a word, which means that it's probably approaching 0. This is a rule we're going to use, that anytime you have a number over x, its limit will be 0. So here is the rule. The rule is that the limit as x approaches infinity of 1 over x to any power is 0, whether it be from the positive direction or the negative direction. we're going to use that rule to help us with a limit problem that's actually really easy to solve if you just think about it in terms of horizontal asymptotes. But I'm going to show you another way of doing it. So let's look at example 2. I want to evaluate the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. I can tell you right away the answer is 3/5. And the reason I can tell you the answer is 3/5 is because it's just a horizontal asymptote. And if the biggest exponent of x in the numerator and denominator is the same, then the limit, or the horizontal asymptote, is the ratio of the coefficients in front of them. Let me show you the algebraic way of doing it. The algebraic way of doing it is to take the biggest exponent of x and divide everything by that exponent. So we're going to divide every term by x squared. If I divide everything by x squared, every term, I'm going to get 3 minus 1 over x minus 2 over x squared in the numerator. In the denominator, I'm going to get 5 plus 4 over x plus 1 over x squared. The rule on the previous page, let's go back, says that any time you have a number over x to some power, its limit in either direction is going to be 0. So this goes to 0, this goes to 0, this goes to 0, this goes to 0, and what are you left with? You're left with 3 over 5. Now again, why would you do it that way if you know the answer is 3/5 because of the rules for horizontal asymptotes? I don't know why, but you'll probably see this again in calculus. Now let's look at something else that we're probably going to just graph. Now, you may remember what the graph of e to the x looks like. It was an exponential function, and you would use that second function above ln if you want to put it in your calculator. And the graph pretty much looks like this. Now, we're only looking at this from one direction. We're looking at it in the negative direction. And if you look at the graph, you should hopefully understand why. The reason we're looking at this in the negative direction is because the limit in the negative direction is going to be 0. Okay, that's pretty easy. What happens if we look at it for the positive direction? Well, if we look at in the positive direction, we go in the positive x direction, what's happening to the y values? Well, they're going up and up and up and up and up forever, which means that the limit is infinity. There really isn't a limit. It doesn't exist. This is getting bigger and bigger forever. So for this particular function, instead of looking at the limit from both directions, we only looked at the limit in the negative x direction, because that one actually had a limit. The positive x direction doesn't have one. Let's do another one. Remember, in order to graph a trig function, you need the calculator to be in radian mode. And anything else, it doesn't matter. So I'm going to graph sine of x. Oops, clear, 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 clear. And you may remember what the graph looks like. We've done it before. The graph of sine looked like this, which means it looks like this in this direction. And the graph of sine, as you may recall, oscillates between 1 and -1. So if we look at what happens as we go in the positive x direction, is our graph converging on a number? Well, it's not going down to 0 and staying there. It's not going to like 1 or -1 and staying there. It's going back and forth. And when a graph oscillates like this between two numbers, we're going to say that there is no limit as x approaches infinity, no matter what way we try to cut it. So we would write dne. Back in chapter 12, we talked about sequences. It's been a while. We did this first semester. And let's look at a to the n equals n over n plus 1, which is a very stereotypical sequence. It's one we run across quite often. If we want to find the limit as n approaches infinity, we're going to find out that the answer is 1. How do I know that? Because if the biggest exponent of the variable in the numerator and denominator is the same, then the horizontal asymptote, which is also the limit as x approaches infinity, is just the ratio of the coefficients. I know, I keep repeating that over and over again. So, what is happening, what we say is happening, is that this is convergent. Convergent is when your outputs approach a single value. I don't know if that's how the book describes it, but what would happen is if you were to look at the graph of this, remember it's a sequence, which means it's a bunch of dots on a graph, what you would see is something that looks like this. It'd start at 0 and it would, oops, I should use a different color. It would start at 0 and it would go up this way, like that. Now, if you actually graph this in your calculator, you're going to see more to this graph. But as we learned with sequences, the smallest number you can plug in for n is 0, and every number that you plug in has to be an integer. So I really shouldn't say it's a graph. Really what it is a bunch of dots doing this, like this. But not all sequences, or any function for that matter, approaches a value. Sometimes the limit just doesn't exist. And we say that's divergent, when the limit does not exist. So let's look at this sequence. Let's look at the limit as n approaches infinity of 1 plus n over n plus n squared. Now, if you look at the biggest exponent of n in the numerator and the biggest exponent of n in the denominator, when the denominator was bigger than the numerator, the horizontal asymptote was y equals 0. So the limit of this sequence should be 0. Now, we can do this algebraically if we divide every term in the fraction by the biggest exponent, which is 2. So I divide everything by n squared. So I get 1 over n squared plus 1 over n in the numerator, and I get 1 over n plus 1 in the denominator. We said that any number over the variable, its limit would be 0. So this is 0, this is 0, and this is 0. And you end up with 0 over 1, which is 0. Or, if you were to graph that expression, matter of fact, I'd do it another way. I could factor out an n, and you'll notice that this goes away and you're left with 1 over n. And anytime you have 1 over a variable, its limit is just going to be 0 as n approaches infinity. This is one that tends to pop up often, or this particular expression ends up in some other equation. Let's look at a to the n is equal to negative 1 to the nth power, and we want to determine if it's convergent or divergent. Well, let's look at what happens as we plug in numbers for n. So negative 1 to the 0 power is 1, because anything that's 0 power is 1. Negative 1 to the first power is negative 1. Negative 1 squared is 1. Negative 1 to the third power is negative 1. Negative 1 to the fourth power is 1. Wait a second, look at what's happening here. It went down, and then it went up, and then it went down, and then it went up, and it's always going up and down to the same number. That's because it oscillates. And if it's oscillating, it's not going to any limit. And if it's not actually approaching a limit, the limit does not exist, therefore it is divergent. Not the book. Divergent, the mathematical principle. Alright, now let's do something a little more extravagant. And I know this looks nasty, but we're going to use simple algebra concepts in order to simplify it. We want to find the limit of the sequence 15 over n cubed times n plus 1, 2n plus 1, all over 6. This is very similar to sequences we ran across in chapter 12 when we did our chapter on sequences and series. So this is what we're going to do. Because everything is either multiplication or division, and there's only addition in parentheses, I can rewrite this expression. So I'm going to rewrite 15 over 6 together here. And then that n cubed, which is n times n times n, I can do this. And again, the reason that I can do this is because, there we go, I'm just rewriting stuff over multiplication and division. If I were to multiply this all back together, I'd still get that original sequence. Now the reason I wanted to look at that is because now n over n is 1, right? So that just kind of goes away. And then, if I want to find the limit of everything, well, I don't have to do anything here with 15 over 6 other than reduce it to 5 over 2. I'm going to rewrite this as 1 plus 1 over n. The reason I can do that is I can divide this by n, divide this by n. And then the third one I'm going to rewrite as 2 plus 1 over n. Now when I go find the limit as n approaches infinity, this is 0, this is 0, and then all I have to do is 5 over 2 times 1 times 2, which is just 5. So the limit of that sequence is 5. And that is finding limits at infinity and limits of sequences.